Tonight, the solar neighbourhood comes into view through an unfamiliar ruler measured by light, instead of footsteps and roads. A light year sounds like time, yet it names a distance. This single correction quietly rearranges the map of space. A year becomes a length becomes a way to keep numbers from dissolving into noise. In calm scientific language, a light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers each second. That speed stays the same in empty space. It stays the same near planets and far beyond them. With that constant speed, 1 year of travel becomes about 9.46 trillion kilometers. The figure is precise enough for astronomy and too large for ordinary intuition. Intuition has an edge. Past that edge, the mind cannot feel the size of a number. It can only follow steps and comparisons. A slow image helps. A dark room holds a thin beam from a small lamp. Dust floats through the beam. Each speck brightens for an instant and fades. The beam seems immediate, yet every point of that beam arrives after a tiny delay. Light has speed even when it feels instant. The same rule stretches outward. A nearby wall is reached almost at once. A distant world is reached later. Distance and delay are tied together by a constant pace. The pace is so high that everyday life hides it. The hiding is not a mystery, it is only scale. A useful scale begins with something small. A single second is short. In that second, light covers about 300,000 kilometers. That is close to 8 loops around Earth's equator. The comparison is simple, yet it already strains imagination. 8 Earths in 1 second feels like a trick. It is only the result of a fast constant multiplied by 1. A clean mental picture follows. A bright ribbon wraps around the planet. The ribbon tightens and closes, then closes again, then closes again. It repeats without effort. The ribbon does not speed up or slow down. The planet simply yields to the pace. The next step is a minute. 60 seconds join into 1 minute. Light crosses about 18 million kilometers in that time. A day adds another layer. 24 hours of that pace becomes about 25.9 billion kilometers. These numbers grow quickly because time stacks neatly. The mind prefers stacking to leaping. A staircase is easier than a cliff. A slow clock image fits here. Sand falls through a narrow neck. Each grain is a second. A minute is a small heap. An hour is a larger mound. A day is a bag of sand. The year is a warehouse. The warehouse still contains ordinary grains. It only contains too many of them for counting by hand. That is the first limit of intuition. Counting fails long before physics fails. An observer can still reason. The reasoning uses anchors. One anchor is the sun. Sunlight reaches Earth in a little over 8 minutes. That means the sun seen at any moment is the sun as it was 8 minutes earlier. That is not dramatic. It is simply built in. If a change happened at the sun, the information would arrive later. The same quiet delay appears at the moon. The moon is seen about a second in the past. The delay is small enough to ignore in daily life and large enough to matter in spaceflight. Radio signals travel at light speed. Commands sent to distant spacecraft are never instant. That practical detail carries a deeper meaning. Space is not a stage where everything shares the same now. Space is stitched to time by the speed of light. The stitch is tight near home because distances are small. The stitch loosens across the solar system. Across the stars it becomes impossible to ignore. Another image helps. A large calm lake holds a single stone dropped at one edge. Ripples move outward. A second stone dropped far away sends its own ripples. Where the ripples meet, patterns form. Information travels across the surface at a fixed speed. Nothing on the lake receives the disturbance before the ripple arrives. Light behaves like that, but in 3 dimensions and with an extreme pace. The year light travels is the unit called a light year. The word year remains only as a convenient way to say this much travel at that constant speed. A second human limit appears here. Large numbers feel interchangeable. Million, billion, trillion can blur into the same vague category of huge. Yet the gaps between them are immense. A trillion is 1,000 billions. A billion is 1,000 millions. Each step is a 1,000-fold jump. The jump matters. If 1 kilometre is imagined as a quiet walk of 10 minutes, then 9.46 trillion kilometres is not a longer walk. It is a different kind of quantity. It cannot be travelled in a lifetime at ordinary speeds. Even the fastest human spacecraft do not make a dent in that scale. The point is not hopelessness. The point is measurement. Astronomers need a unit that matches the size of their map. Kilometres remain correct, but they have become unreadable. A distance to a nearby star written in kilometres becomes a string of digits with little shape. Written in light years, it becomes a small count that can be compared at a glance. 4 light years versus 40 light years is immediately 10 times farther. The unit restores proportion. It also carries an extra meaning. The number of light years to an object is also the number of years that light has been travelling. A star at 4 light years is seen as it was 4 years ago. A star at 500 light years is seen as it was 5 centuries ago. The sky becomes an archive. The archive is not metaphorical, it is literal physics. Photons leave a source and take time to arrive. Between departure and arrival, the universe changes. Most stars change slowly, some change quickly. Either way, the view is always delayed. A still visual anchor settles the thought. A quiet gallery holds paintings behind glass. Each painting shows a moment that is already finished. The glass is the travel time. The eye sees the image now, yet the moment belongs to then. The next sections build the staircase more carefully. The steps will move from seconds to minutes to hours with gentle repetition. The scale will reach beyond planets and toward the nearest stars. A light year will stop being a single intimidating number. It will become a familiar rung on a ladder. If this kind of calm science narration feels useful, a single like or subscription can support more nights like this. A calm progression continues by shrinking the scale again before expanding it. The unit of 1 light second is small enough to picture and large enough to impress. In 1 second, light travels about 300,000 kilometres. That distance is close to 3/4 of the path to the Moon. The Moon orbits Earth at an average distance of about 300 to 84,000 kilometres. Light needs a little over 1 second to cross that gap. The number is simple. The implication is steady. Even the nearest celestial body is separated by a measurable delay. A practical consequence appears in space missions. Radio signals sent between Earth and lunar spacecraft take about 1.3 seconds each way. A message travels outward. A reply returns later. The pause is short, yet it cannot be removed. No adjustment in equipment can erase it because it is set by the speed of light. That speed is not a convenience, it is a boundary. A clear visual anchor steadies the idea. A large parabolic antenna stands against a dark sky. Its surface curves inward like a shallow bowl. It points toward a small bright disk above the horizon. The dish does not shout or move rapidly. It listens and waits. The waiting is built into the distance. The next rung on the scale is a light minute. 60 light seconds join to form it. In 1 light minute, light travels about 18 million kilometres. That is a span far beyond Earth and Moon. The Sun is about 150 million kilometres away from Earth. Sunlight takes roughly 8 minutes and 20 seconds to arrive. That is just over 8 light minutes. The comparison is steady and useful. The Sun is 8 light minutes distant. This fact reshapes the meaning of now. The Sun seen in the sky is not the Sun of the present instant. It is the Sun of 8 minutes earlier. The delay is harmless in daily life. It becomes important in careful measurement. Solar flares and changes in brightness are detected after that short journey. Instruments do not receive events as they occur. They receive them as they arrive. A gentle image holds the concept. A filtered solar disk glows through a thin veil of atmosphere. Its edge trembles slightly due to air turbulence. The trembling belongs to Earth's air. The light belongs to the Sun of minutes ago. 2 places, 2 times joined by a constant speed. The scale continues outwardly. A light hour equals 60 light minutes. That is about 1.08 billion kilometres. Some outer planets approach this distance from Earth at certain points in their orbits. Saturn, for example, can be a little over 1 light hour away when conditions align. When a spacecraft orbits Saturn, signals exchanged with Earth may be delayed by more than an hour each way. The delay shapes mission design. Commands are not sent casually. They are planned and uploaded in sequences. There is a limit of control here. No human operator can steer a probe in real time across such distances. The gap between action and confirmation is too large. Spacecraft require onboard autonomy. They must recognize faults and respond before instructions arrive. The speed of light sets that operational boundary. A quiet visual supports the idea. A pale ringed planet floats in black space. Thin shadows fall across its rings. A small probe circles it. Between the probe and Earth lies an invisible thread of radio waves. The thread has length. The length has time. The notion of a light day adds another layer. 24 light hours become about 25.9 billion kilometers. The most distant human-made object, Voyager 1, is roughly a light day from Earth. Signals take about 24 hours to travel one way. A simple exchange of command and confirmation spans nearly 2 days. The spacecraft drifts through a region where the solar wind thins and merges with interstellar space. The boundary is called the heliopause. It is not a sharp wall. It is a gradual transition zone where charged particles slow and mingle. The scale shift from seconds to days reveals a pattern. Each multiplication of time multiplies distance by the same steady factor. The mind struggles when the factors stack. It helps to re-anchor the idea in something repetitive. A metronome ticks once per second. Each tick marks another 300,000 kilometers. After 60 ticks, a light minute has passed. After 3,600 ticks, a light hour has passed. After 86,400 ticks, a light day has passed. The numbers are large, the ticks are simple. A limit of perception appears again. There is no sensory cue for these distances. No wind changes, no colour shift. Only instruments and reasoning reveal the delay. Human experience evolved on scales of meters and hours. It did not evolve to sense millions of kilometers. Another visual anchor closes this section. A dark expanse holds a faint golden point that represents the sun seen from far beyond the outer planets. It no longer dominates the sky. It resembles an ordinary star. The solar system compresses into a small region around that point. Distance flattens perspective. The ladder of light units now feels as less abrupt. Seconds, minutes, hours, and days create a rhythm. That rhythm prepares the way for the larger leap to the light year. The next step will gather these smaller intervals into a single expansive measure. A stable reference point in the solar system helps the scale feel real. The sun sits at a distance where light still needs time. Sunlight reaches Earth in about 8 minutes and 20 seconds. That delay is short enough to ignore and large enough to matter. It defines the first clear boundary between daily instinct and cosmic measurement. The sun is not seen as it is right now. It is seen as it was a little over 8 minutes earlier. The statement sounds philosophical, yet it is only geometry and speed. Light leaves the solar surface and travels through space. It arrives later with information that is slightly old. A slow visual anchor settles the thought. A bright disk hangs low behind thin clouds. The edge of the disk shimmers as warm air rises. The shimmer belongs to air. The light belongs to a solar moment already finished. This simple delay changes how distance is narrated. It also changes how events are timed. A solar flare occurs. The eruption launches particles that travel far slower than light. The visual flash is detected after 8 minutes and 20 seconds. The charged particles arrive much later, often tens of minutes to days after the flare. 2 streams leave the same source. One stream carries images and measurements quickly. The other stream carries matter slowly. The difference becomes useful for planning and protection. It also shows that arrival depends on what is travelling. The same logic applies to the rest of the solar system. Any signal sent outward travels at light speed. Any reply returns at light speed. Every round trip has a built-in weight. The weight is not a technical flaw, it is the space itself. This is where the light-based units begin to feel necessary rather than decorative. A minute light is not only a number, It is a minimum delay for information across that distance. Mars provides a clean example because it moves closer and farther with its orbit. At favourable alignments, Earth and Mars can be about 2 light-minutes apart. At unfavourable alignments, they can be about 22 light-minutes apart. The numbers vary with date, yet the principle stays still. Command signals sent to a rover never arrive instantly. A rover does not respond in the same moment. Planning becomes a choreography of waiting. Another visual anchor supports the practical angle. A small rover sits on rust-coloured ground. Its shadow falls sharply in thin air. A mast camera points toward a pale sky. In that quiet scene, every instruction arrives late. Every image returns late. The delay does not feel dramatic. It feels like distance made visible in time. A limit of control appears again. If a wheel slips on loose soil, Earth cannot correct it immediately. Engineers design safe paths. They send sequences of actions. They wait for confirmation. The rover carries a measure of autonomy. It can pause if it senses danger. It can preserve itself while Earth waits for new information. This pattern repeats across deep space missions. It is the same reason that outer planet spacecraft follow long preloaded plans. The speed of light makes real-time piloting impossible beyond a certain point. This is not a failure of human skill. It is a feature of the universe. The Sun also makes another lesson clear. A unit based on light ties distance to a familiar clock. 8 minutes is an ordinary interval. It can be held in attention. It can be compared with cooking time or a short walk. The Sun sits at a distance that feels vast in kilometers. It feels manageable in light minutes. The conversion is calming. It gives the mind a handle. It turns 150 million kilometers into a short span of time, yet it does not change the distance itself. It only changes how it is carried in thought. The next step is to keep building that handle with gentle repetition. A light second already reaches beyond the moon. A light minute reaches far into the inner solar system. A light hour reaches toward the outer planets. A light day reaches into the outskirts of the solar wind. Then the idea of a year begins to loom. A year is familiar. Seasons cycle, calendars fill, holidays return, and the length of a year is a human rhythm. Light turns that rhythm into a cosmic ruler. A year of light travel becomes a long straight line through emptiness. Another visual anchor offers a quiet way to imagine it. A long corridor stretches through darkness. Small lights mark equal intervals along the floor. Each light is a minute. Groups of lights form an hour. Groups of hours form a day. The corridor continues until the markers become too dense to count. The corridor remains the same corridor, only the scale changes. That corridor is not a real tunnel. It is a way to let repetition replace shock. A limit of observation also comes into focus near the Sun. The Sun is close enough to show fine detail with instruments. Granulation patterns cover its surface. Dark sunspots form and drift. A thin edge called the limb appears slightly darker due to how light escapes from different depths. These are physical details, not metaphors. They exist because hot plasma rises and falls. They exist because magnetic fields thread the surface. Even here, seeing is delayed by minutes. Even here, the present is slightly behind the source. The same rule holds for everything else. Distance always means looking backward in time. The time is small for nearby objects. The time becomes large as distance grows. That is the second reason light-based units are so useful. They not only make distances readable, they also remind the mind what information can and cannot do. Information cannot outrun light. No telescope can show an event before its light arrives. No radio receiver can hear a transmission before the wave reaches it. The universe enforces patience. A final visual anchor for this section holds that patience in a single image. A quiet observatory dome stands on a high ridge. The dome opens like a curved eyelid. The telescope inside points toward a bright point near dawn. The instrument waits without urgency. It collects photons that have already travelled. It turns them into knowledge only after they arrive. The next section moves back toward the moon for a moment. It returns to the simplest delay, the delay that can be heard in mission recordings and measured in seconds. From there, the ladder continues upward toward the full measure of the light year. The Moon offers a clean scale because it sits close enough to feel familiar and far enough to enforce delay. The average distance is about 384,000 kilometers. Light takes a little over 1 second to cross that gap. Radio signals, which are also electromagnetic waves, obey the same limit. A message sent to the Moon arrives about 1.3 seconds later. A reply returns another 1.3 seconds after that. A simple exchange carries a pause of nearly 3 seconds. The pause is not caused by equipment, it's caused by distance. A calm physical detail makes the idea concrete. A spacecraft orbiting the Moon passes through alternating sunlight and shadow. The line between day and night on the surface is called the terminator. Near that line, craters cast long shadows that stretch like dark wedges. The light that creates those shadows does not appear instantly. It streams in at a fixed speed. The same speed carries radio words between a pilot and a controller. The Moon is close enough to show the limit clearly without drowning the mind in huge numbers. A quiet visual anchor fits here. A pale lunar disk hangs above a low horizon. The surface looks textured. Dark maria spread like smooth stains. A thin bright rim outlines the curve. The disk appears immediate and still. The delay is hidden behind that stillness. This is where a practical limit of operation becomes easy to describe. A remote-controlled car on Earth can be driven in real time because the delay is tiny. A rover on the Moon could be driven almost in real time, yet the 1.3 second lag would still make steering feel sluggish. A rover on Mars cannot be driven that way at all. The delay there is minutes. The Moon sits between those worlds as a teaching distance. It shows how even small lags change behavior. The next rung of scale is the light minute. In a single light minute, light travels about 18 million kilometers. The Moon becomes a tiny step inside that span. The mind senses the compression. A distance that once felt enormous becomes a fraction of a larger unit. That is the pattern that will repeat many times. Each new scale makes the previous one feel smaller. The effect is not meant to dismiss the earlier distance. It is meant to prepare for the much larger distances between stars. A limit of intuition appears again with a simple numerical contrast. A car at highway speed might travel about 100 kilometers in an hour. Light travels about 1.08 billion kilometers in an hour. The ratio is so large that it stops behaving like an ordinary comparison. The only way to carry it is to choose an image and keep it steady. A useful image is the idea of circling Earth. Light circles Earth about 7.5 times in 1 second. A car cannot circle Earth even once in a day. The contrast is not about cars, it is about what fast means at different scales. A physical detail from spaceflight adds texture without drama. Communication delays do not only affect conversation, they shape how spacecraft are kept safe. Craft cannot wait for Earth to diagnose every anomaly. It must sense low power overheating or attitude drift and correct itself. It enters a safe mode. It points its antenna toward the Earth. It reduces activity, then it waits for instructions that arrive later. This behavior is common across deep space missions. It is a direct response to the finite speed of light. A visual anchor supports this safety idea. A small probe drifts in darkness. Its solar panels are thin rectangles. One side is lit, the other side fades into shadow. A gentle rotation keeps the antenna aligned. The craft is quiet. It holds itself steady while a signal travels across space. Now the ladder can move in a smooth way from seconds to hours to days. A light hour is about 1.08 billion kilometers. A light day is about 25.9 billion kilometers. The numbers are large. The meaning is simple. A light day is the distance light travels in 1 day. It becomes a way to speak about the outskirts of the solar system and the region where spacecraft like Voyager operate. A light day is also a way to speak about latency. A one-way message to a spacecraft 1 light day away takes 1 day. A two-way exchange takes 2. A limit of observation becomes sharper at these distances. The sun still dominates brightness from within the inner solar system. Farther out, the sun shrinks into a bright point. The sky becomes more uniformly dark. Stars appear without the haze created by Earth's atmosphere. Yet the human mind still expects closeness because the sun can still be seen. That expectation is misleading. Vision does not measure distance in space. It measures angle and brightness. Brightness can fall with distance, but it also depends on intrinsic power. Stars of different luminosities can look similar. That is why distance needs a separate ruler. Light-based units are part of that ruler. A quiet, everyday comparison helps hold the number without strain. A 1-second delay is like a small pause in a phone call. A 1-minute delay is like waiting for a kettle to begin to hiss. An hour delay is like waiting for bread to rise. A day delay is like sending a package and watching tracking updates that move slowly. These comparisons do not convert kilometers into emotions. They convert delay into something the mind can place within routine. The light year will later be treated the same way as a long delay that becomes a usable ruler. A final visual anchor closes the section and prepares the next step. A thin thread of light stretches from Earth to the Moon. It is not visible in reality yet. It can be imagined as a straight taut line. Along that line, a pulse moves outward. The pulse reaches the Moon. It reflects as a reply. It returns. The pause is always the same. The pause is distance made audible. The next section will gather the ladder into a full year. Seconds, minutes, hours, and days will stack into a single measure. The number 9.46 trillion kilometers will be allowed to settle as a consequence of steady multiplication rather than as a shock. A light year becomes easier to hold when it is built from smaller units already familiar. A year contains 365 days. Each day contains 24 hours. Each hour contains 60 minutes. Each minute contains 60 seconds. Light travels about 300,000 kilometers each second. The multiplication is calm. The result is enormous. 1 year of a light travel becomes about 9.46 trillion kilometers. The value can be stated and then set aside. The important part is the structure. A constant speed multiplied by a familiar calendar creates a ruler that fits cosmic distances. A quiet visual anchor helps this structure feel steady. A long strip of paper lies on a table. Small marks are placed at equal intervals. Each mark is a second. Groups of marks form minutes. Groups of minutes form hours. Groups of hours form days. The strip continues until it curls off the table and disappears. The marks never change. Only their count grows beyond what the eye can track. A limit of intuition appears here in a precise way. The mind is comfortable with thousands. It struggles with millions. It loses shape with billions. A trillion is not just bigger. It is 1,000 times a billion. The jump breaks ordinary sense. A useful comparison uses time instead of distance. 1 million seconds is about 11.6 days. 1 billion seconds is about 31.7 years. 1 trillion seconds is about 31,700 years. The numbers share the same words, yet their scale is wildly different. This is why astronomers avoid writing star distances in kilometers. The digits become long strings without grip. The light year restores grip by compressing the same information into a small count. A nearby star can be described with a handful of units rather than with a parade of zeros. Proxima Centauri is about 4.24 light years away. Written in kilometers, it is about 40 trillion kilometers. Both are correct. One is readable, the other is heavy. A physical detail adds texture to this unit choice. Distance to stars is often measured by parallax. As Earth moves around the Sun, a nearby star appears to shift slightly against the distant background. The shift is tiny. It can be less than the width of a human hair seen from kilometers away. Instruments measure that shift. Geometry turns it into distance. The unit used afterward is a matter of clarity. Light years present the distance in a human-friendly size while remaining anchored in physics. A visual anchor fits the parallax idea. 2 photographs are imagined taken 6 months apart. In each image, a nearby star sits slightly to one side relative to the same distant pattern. The shift is subtle. It is real. It is the signature of Earth's orbit acting as a baseline. The light year also carries an extra benefit. It ties distance to look-back time. A star at 4.24 light years is seen as it was 4.24 years ago. The statement is not poetic. It is direct. The photons reaching Earth tonight left that star years ago. They crossed darkness without stopping. They arrived now. The now at Earth is not the now at the star. The separation is built into space itself. A limit of observation becomes important at this point. A telescope cannot see beyond the arrival of light. Even the largest mirrors cannot collect an event before it sends its photons. No technology can reverse that. The most advanced camera only changes how many photons are captured and how well they are sorted. It does not change when they arrive. The speed of light creates a horizon for information. The horizon moves outward as time passes, but it cannot be skipped. A calm image holds this. A closed book sits on a shelf. Pages contain events. The only way to read a page is to open it. Light is the opening of pages in the universe. The pages cannot be opened before the light arrives. The shelf is the distance. The opening is the delay. The light year can now be placed on the ladder already built. 1 light second is 300,000 kilometers. 1 light minute is 18 million kilometers. 1 light hour is 1.08 billion kilometers. 1 light day is about 25.9 billion kilometers. Multiply a light day by 365 and the light year emerges. The progression is not meant to overwhelm. It is meant to show continuity. The same constant speed creates every unit. A practical sense of scale can be added with one more grounded comparison. The distance from Earth to the Sun is about 8.3 light minutes. That means 1 light year is about 63,240 times the Earth to Sun distance. The solar system feels large, yet it fits inside a tiny fraction of a light year. Even the most distant planets orbit within a small slice of that unit. The gaps between stars are measured in multiple light years because space between stars is mostly empty. A visual anchor fits the emptiness. A black sea holds scattered small islands of light. Each island is a star. Between islands is vast dark water. The islands are not crowded. They are separated by long stretches and nothing. The light year becomes the natural unit for measuring those stretches. The section ends with a gentle preparation for the first nearby destination beyond the Sun. The next step will approach the nearest stars not by jumping straight to huge numbers, but by using light years as a calm counting system. The first star distances will be small in light years, yet they will still represent an extreme separation from the solar system. The first destination beyond the solar system is not a planet. It is another star, and the distance to it is naturally measured in light years. The nearest star system includes Alpha Centauri, a group of stars bound together by gravity. Within that system, Proxima Centauri is the closest star to the Sun. The distance is about 4.24 light years. In kilometers, that is about 40 trillion. In light years, it is a calm number that fits on the tongue and in the mind. A useful everyday comparison follows immediately. 4 years is the span of a school cycle. It is the span between major life chapters. It is long enough for seasons to repeat several times and short enough to remain personal. Light years translate a distance into a time-like span without becoming a time unit. The span does not mean travel time for spacecraft. It means travel time for light. That distinction stays central. A quiet visual anchor supports this. A dim red point sits near brighter stars. It is not visible to the unaided eye, yet it exists as a neighbour. In a telescope, it appears as a small, steady glow. It does not look close. It looks like a star. Its closeness must be learned through measurement, not through sight. A limit of perception becomes clear. Brightness does not reliably indicate distance. A luminous star far away can look like a faint star nearby. The human eye has no built-in parallax sensor for the night sky. The brain does not receive the baseline necessary to infer distance. That is why astronomy relies on geometry, motion, and calibrated light. A light year is part of this calibrated language. The scale of travel can now be stated in a way that remains calm and factual. The fastest spacecraft humans have built achieve peak speeds on the order of a few hundred kilometers per second under special conditions. Even at such speeds, reaching Proxima Centauri would take thousands of years. This is not an expression of despair. It is a measure of scale. Space between stars is wide, it turns human engineering into slow drift. A physical detail adds texture to the idea of wide space. Between stars lies the interstellar medium. It is thin, it contains gas and dust, often only a few particles per cubic centimetre. Yet at high speeds, even thin material can matter. A small dust grain at a large fraction of light speed would carry enormous kinetic energy. This creates a limit not only of propulsion, but of shielding. The distance is not the only barrier. The environment becomes a hazard when speed rises. A visual anchor supports this without drama. A tiny craft moves through a dark field. Occasional faint specks pass like distant snow. The craft is protected by a forward shield. The shield is thin and layered. It is designed to absorb impacts that are unlikely but consequential. The scene remains quiet, but the engineering problem is clear. The light year also improves comparison within the local neighbourhood. A star at 8 light years is about twice as far as Proxima Centauri. A star at 40 light years is about 10 times as far. These ratios become simple. In kilometres, the ratios remain the same, but the numbers are harder to hold. The unit does not change reality, it changes readability. A limit of intuition appears again in the notion of near. Within the Milky Way, a star 4 light years away is extremely near. Within human experience, it is unimaginably distant. Both statements can be true because each uses a different reference scale. The galaxy is about 100,000 light years across. A handful of light years is a small fraction of that. Yet a handful of light years is far beyond any direct travel capability. A calm physical detail about stellar motion adds a sense of time. Nearby stars move relative to the Sun. Their positions shift slowly over centuries. Proper motion can be measured as a tiny drift across the sky. Barnard's star, for example, has a very large proper motion compared to most stars. Over a human lifetime, its shift can be detected with careful imaging. The movement is real, but it is slow in angular terms because distances are large. Even when a star is moving fast through space, the separation is still counted in light years. A visual anchor fits the idea of motion. A star field is photographed in black and white. One star is marked with a small circle. A decade later, another photograph is taken. The circled star has shifted slightly against the pattern. The shift is small, almost delicate. It hints at long durations and wide spaces without any need for large numbers. The ladder of scale can now widen from single stars to small neighbourhoods. Within about 20 light years, there are many star systems. Some are single. Many are binaries, some are triples. Most nearby stars are red dwarfs, smaller and cooler than the Sun. These stars are common. They're also faint. That is why the night sky, seen with the unaided eye, is dominated by rarer, brighter stars. The visible sky is not a fair census. It is a selection bias. A limit of observation appears as a quiet warning. What is easily seen is not always what is most common. Brightness skews perception. Light years and careful measurement correct that skew. A final visual anchor closes the section with calm continuity. A map is imagined as a 3-dimensional lattice of points. Each point is a star. Lines between points are not drawn because the lines would dominate the page. Instead, the map uses distance rings measured in light years. The nearest ring encloses a few neighbours. The next ring encloses many more. The mind begins to read space as a structured neighbourhood rather than as an empty abyss. The next section will shift from space as distance to space as history. The connection between light years and looking into the past will become clearer through a few nearby examples chosen for stability and gentle perspective. A light year quietly turns the night sky into a record of earlier moments. The mechanism is simple. Light takes time to travel. A star seen from Earth is seen as it was when its light began the journey. If the star is 8.6 light years away, the arriving photons left 8.6 years ago. The star may be stable and nearly unchanged. The delay still exists. The sky becomes an archive that updates at the speed of light. A calm example is a bright nearby star. Sirius is about 8.6 light years away. Sirius appears brilliant in the night sky because it is relatively close and intrinsically luminous. Yet the light entering an eye tonight began its travel years ago. The effect is not dramatic in daily life, it is conceptually important. Seeing does not mean seeing the present, it means receiving light that has already travelled. A visual anchor helps hold the idea without strain. A bright white point hangs in a dark sky and it twinkles softly due to atmospheric turbulence. The twinkle is a local effect. The light itself has crossed years of empty space. The point looks immediate. The journey behind it is long. The next example can be slightly farther and still gentle. Vega is about 25 light years away. That means the light arriving now left around a quarter century ago. A quarter century is a span with human meaning. It contains childhood, adolescence, and adulthood. It contains many changes on Earth. Vega itself changes very little on that timescale, yet the view is still delayed. The delay is not about change. It is about connection between distance and information. A limit of intuition appears here. Human language often treats now as shared. In astronomy, now is local. It applies to the location of the observer. Far away, the same word points to a different slice of time. This is not philosophy. It is communication speed. Two places cannot share an instantaneous present if signals take time to move between them. A physical detail can make the archive feel more real. Light is carried by photons. Photons are quanta of electromagnetic radiation. They do not age during their travel in the ordinary sense. They simply propagate through space. Along the way, they can be absorbed, scattered, or redshifted by cosmic expansion over extreme distances. In nearby space, the main story is simple propagation. The photons that arrive are survivors of a long straight trip. A visual anchor fits this particle view. A long dark hallway is imagined with a single faint sparkle moving along it. The sparkle is not a bead rolling, it is a pulse of light. It does not slow, it does not tire, it simply crosses the corridor. The corridor is space, the sparkle is information. The archive idea that becomes richer with a more distant star that is still visible and culturally familiar. Betelgeuse is hundreds of light years away. Estimates vary and the exact distance is refined as measurements improve, but the scale remains centuries. That means the light reaching Earth now left the star centuries ago. When the photons began their journey, the world on Earth was very different. This does not change what the star is doing now, it changes what can be known now. A limit of observation appears sharply here. A star can change or even end its life, and distant observers will not know until the light of that change arrives. Supernovae, for example, can be seen in other galaxies as sudden bright points. The explosion itself is the moment of change at the source. The observation is delayed by the travel time. In the sky, the event appears when it arrives, not when it occurs. A calm physical detail about stellar evolution can be included without tension. Massive stars burn fuel quickly. They can swell into red supergiants. Their outer layers can become unstable. Eventually, their cores can collapse. This process can end in a supernova. The timescales inside a star can be long or short depending on the phase. For distant observers, the key timescale is still the light travel time. A visual anchor supports this without dramatizing. A red star appears slightly warmer in color than its neighbors. Its light looks soft rather than harsh. The surrounding constellations remain still. The star seems peaceful. The archive principle suggests only that the view is delayed, not that catastrophe is imminent. The archive idea also changes how the Milky Way is understood. The center of the galaxy lies about 26,000 light years away. If the dust between stars did not block the view, the light from the center would be seen as it was tens of thousands of years ago. That was long before agriculture, writing, and cities. Human history fits inside the time it takes light to cross a small fraction of the galaxy. This is a scale shift that can be felt even if it cannot be fully imagined. A limit of perception appears in a quiet way. Large distances make large times unavoidable. A mind that thinks in years and decades encounters a sky that speaks in centuries and millennia. The light year becomes not only a distance unit, but also a reminder of that temporal depth. A final visual anchor closes the section with softness. A clear night reveals a broad milky band. Dark lanes cut through it where dust blocks starlight. The band is a cross-section of the galaxy. Each point of light within it carries a different age. Some photons have travelled a few years, some have travelled thousands. The sky becomes layered time. The next section will return to the measurement side. It will describe how the speed of light was first inferred from careful observation and why instantaneous light was replaced by a measurable finite speed. The tone remains calm. The focus remains on astronomy and deep space scale. The finite speed of light was not always accepted. For a long time, light seemed instantaneous because everyday distances are small. The shift from assumption to measurement arrived through patient observation and careful timing. A key historical step came from studying the eclipses of Jupiter's moons. These moons pass into Jupiter's shadow at predictable intervals. Over months, the intervals appeared to drift. The drift depended on where Earth was in its orbit. When Earth moved closer to Jupiter, the eclipses seemed to occur earlier. When Earth moved farther, they seemed to occur later. The simplest explanation was not that the moons changed their clocks. The explanation was that the light carrying the event took different amounts of time to reach Earth. The event happened on schedule. The report arrived late. This insight can be held with a quiet visual anchor. A small bright dot circles a larger disk. At certain moments, the dot disappears behind the disk's shadow. A distant observer watches. The disappearance is not delivered instantly. It is delivered when the light arrives. The observer's calendar stays steady. The arrival time shifts with distance. A limit of observation appears here in a precise form. Without a second clock and a changing baseline, the delay would remain hidden. Earth's orbit provided the baseline. Jupiter's moons provided repeating events. Together they created a natural experiment. This method is gentle. It does not require exotic machines. It requires patience and geometry. Modern measurement refined the speed of light with extreme precision. Today the value is fixed by definition in the International System of Units. The speed is 299,792,458 meters per second. This exact number is used to define the meter itself. The decision reflects confidence. Light speed in vacuum is treated as a universal constant. It does not drift with season. It does not depend on direction. It is a stable feature of space-time. A physical detail adds texture without complication. In materials like glass or water, light travels more slowly than in vacuum because it interacts with the medium. Photons are absorbed and re-emitted, or more precisely, the electromagnetic wave excites charges that re-radiate, delaying the overall propagation. The constant that defines the light year uses vacuum speed, not material speed. Space between planets and stars is close enough to vacuum that the constant applies cleanly. This keeps the unit stable. A visual anchor supports the medium idea. A beam enters a block of glass. Inside the beam bends slightly. The beam exits and continues. The beam's path changes because the medium changes its effective speed. Outside the block in air and then in emptiness, the pace returns to its vacuum value. The light year depends on both the constant speed and the chosen year length. Astronomy often uses the Julian year for calculations defined as 365.25 days. Many explanations use 365 days for simplicity. Either choice yields a value around 9.46 trillion kilometers. The small difference is not important for intuition. The key is that the unit is anchored in measurable constants. It is not arbitrary, it is not a poetic invention. It is a ruler built from the most reliable speed known. A limit of intuition appears again in the way units are named. The presence of the word year can mislead. A light year is not time, it is distance. The name is a shortcut for the distance light travels in 1 year. The confusion is common because language reuses the same word for the calendar and for the ruler. The correction is simple. The mind can hold it. The unit becomes useful once the correction is internal. A calm, physical detail about measurement of star distances adds realism. Parallax measures nearby stars. For more distant stars, astronomers use standard candles objects with known luminosity, such as certain variable stars and Type 1a supernova. By comparing intrinsic brightness to observed brightness, distance can be inferred. These methods extend the distance ladder beyond parallax. Light years and parsecs then become the language of those distances. Each rung depends on calibration from the rung below. The overall structure is slow, cumulative, and careful. A visual anchor supports the distance ladder. A set of steps rises along a wall. Each step is labelled with a method. The first is parallax. Higher steps use brighter beacons. The top steps reach far into the galaxy and beyond. The steps are not used by climbing in one leap. They are used by stepping, calibrating and checking. The constant speed of light also ties into a deeper idea. Space and time are linked by that constant. In classical intuition, space and time are separate. Distance can be measured independently of duration. In relativistic physics, the speed of light acts like a conversion factor between space and time coordinates. This does not need a heavy derivation to be felt. The earlier examples already show it. A light minute is a distance and a time of travel. A light hour is the same. A light year follows naturally. The unit carries both meanings at once. It says how far and it hints how long information needs. A limit of observation becomes more important at larger scales. When observing distant galaxies, the light has travelled for millions or billions of years. The images are not only distant in space, they are distant in time. Telescopes become time machines in a literal sense. They see earlier phases of the universe. The light year becomes a way to speak about that look back to time without leaving the language of distance. A final visual anchor closes the section gently. A calm night sea stretches to the horizon. A lighthouse beam sweeps across the water. The sweep is slow, predictable, and finite. A boat far away does not see the beam until it reaches it. The beam carries information. The delay is the sea. The universe is larger, darker, and emptier, yet the logic is the same. The next section will approach relativity in a quiet way, focusing on the single idea that the speed of light remains the same for all observers, and how that forces time and distance to adjust. The tone stays neutral and soft. Relativity enters quietly through a single stubborn fact. The speed of light in vacuum remains the same for every inertial observer regardless of how the source moves. In everyday life, speeds add in an intuitive way. A vehicle moves forward, an object is thrown forward inside it, and an outside observer expects the speeds to combine. That expectation works well at low speeds. Near the speed of light, nature refuses that simple addition. The refusal is not a detail at the edge of physics, it is a structural rule. If light always moves at the same speed, then space and time cannot behave as rigid and separate containers. They must adjust. The adjustment is not optional. It is required for consistency. The result is a set of effects that sound strange only because the human mind is trained on slow motion. Time dilation appears. Length contraction appears. The relationship between energy and inertia changes. None of this needs to be treated as spectacle. It can be treated as the universe keeping its own accounting balanced. A useful anchor begins with a calm image rather than an equation. A long train moves through the night. Inside, a small lamp flashes briefly. The flash spreads outward at light speed. From the train's interior, the flash expands symmetrically. From the ground, the same flash still expands at the same light speed. The symmetry is not preserved in the same way because the train moves, yet the speed of the light remains unchanged. The only way both views can remain true is for their measurements of time and distance to differ. In this view, time is not a single shared rhythm, it is tied to motion. The concept feels abstract until a physical consequence is named. Clocks do not remain synchronized across different motions when light speed is held constant. A moving clock as measured from a stationary frame ticks more slowly. The effect is tiny at everyday speeds and large near light speed. A limit of intuition appears at once. Daily experience contains no direct sensation of time dilation. The effect at walking or driving speeds is far below what a human could notice. The phenomenon still exists. It has been measured with precision clocks on aircraft and satellites. It is part of the reason that satellite navigation must apply relativistic corrections. The corrections are not philosophical. Without them, position errors grow quickly. The system works because the physics is real and the accounting is done correctly. A physical detail adds texture. Atomic clocks tick by counting transitions in atoms. These transitions are exceptionally still. When such clocks are compared after one has travelled at high speed or spent time at different gravitational potential, the readings differ in a predictable way. In-orbit satellites move quickly and also sit higher in Earth's gravitational field. Motion tends to slow satellite clocks relative to Earth's surface clocks. Weaker gravity tends to make satellite clocks run faster. Both effects are measurable. Both must be combined. The net correction is applied continuously. This is a quiet demonstration that time is not universal in the old sense. The speed of light remains central because it is the bridge between space and time. In the units used by astronomers, a light second, a light minute, and a light year all convert a time interval into a distance by multiplying by c, the speed of light. In relativity, c also defines how intervals in space and intervals in time combine into a single space-time interval. This is not required to be carried as formula in the mind. It can be carried as a disciplined habit. Anytime a large distance is discussed, a minimum information delay is implied. Anytime a high speed is discussed, the meaning of time passing depends on the frame. A calm example that stays within astronomy helps. Cosmic ray particles strike the upper atmosphere and create muons. Muons decay quickly. At rest, their lifetime is so short that few should reach the ground from high altitude. Yet muons are detected at Earth's surface in large numbers. The explanation is time dilation. In the Earth frame, the muons move near light speed, and their internal clocks run slow. Their lifetime as measured in the Earth frame stretches long enough for many to reach the ground. From the muon's frame, the lifetime remains short, but the distance to the ground is length contracted. Both descriptions agree on the observed result. The universe remains consistent. The human expectation that time and distance are fixed is what fails. A visual anchor helps hold this without drama. A thin veil of atmosphere sits above the planet like a faint blue skin. High above, invisible particles race downward. Their journey is brief in their own frame, yet it delivers them through the entire thickness of air. The ground receives what classical intuition would forbid. Relativity permits it, and measurement confirms it. The speed of light also explains why faster-than-light travel is not treated as a normal engineering challenge. Objects with rest mass require increasing energy to approach c. As speed rises, added energy yields smaller gains in speed. The required energy grows without bound as c is approached. This is not framed as a cosmic punishment. It is framed as the structure of space-time as described by special relativity. Light itself, carried by photons, always travels at c in vacuum. Photons have zero rest mass and cannot be at rest. Massive objects have non-zero rest mass and cannot reach c. This division is not a limitation of engines. It is a property of the world as measured. A limit of observation appears again. No signal, no material object, and no causal influence can travel faster than light in local space-time. This protects cause and effect from paradox in ordinary conditions. It also sets the ultimate boundary for communication across light years. A message to a star system 4 light years away cannot arrive sooner than 4 years by any known mechanism that respects local light speed. That fact is one reason the light year is such a fitting unit. The unit does not merely count distance, it implies a minimum time for information exchange. A calm visual anchor supports this boundary. A quiet line is drawn between 2 points on a dark page. The line is long. A small pulse moves along it at a fixed pace. Nothing at the far end can know of the pulse until it arrives. No effort at the near end can make it arrive sooner. The line is space. The pulse is information. The pace is the constant. Relativity also carries a gentle consequence for imagination of travel. At speeds close to c, time dilation means that travellers can experience less time than those who remain behind. A journey that takes many years in an Earth frame can correspond to fewer years on board a fast spacecraft. This does not remove the light-year barrier for the outside universe. It changes how duration is experienced by the traveller. It also introduces a social separation. Returning from such a journey implies arriving in a future where much more time has passed for those who stayed. The idea can be described without drama as a mismatch of accumulated time due to relative motion. A final physical detail grounds the section in the cosmic theme. Light years remain practical because they speak the language of sea. Stars are separated by multiple light years because space is sparse on that scale. The finite speed of light ensures that observation is always delayed and that the sky is always a record. Relativity ensures that time itself is not a universal background but a measure tied to motion and gravity. The next section will move from these principles back into the quiet craft of astronomy, showing how these ideas shape the way distances, maps and horizons are understood on the largest scales. The light year begins as a practical unit and then quietly becomes a key to the largest maps. Once distance is understood as light travel time, the idea of a horizon becomes natural. A horizon is not a wall. It is a limit set by how far information can reach within a given age of the universe. Light can only travel so fast. The universe has only existed for so long. Those two facts together define what can be seen. The age of the universe is about 13.8 billion years. A first instinct might say the observable universe should be 13.8 billion light years in radius. The real picture is larger because space itself expands while light travels. As photons move, the distance between the source region and the observer can stretch. This is not light slowing down, it is the geometry of space changing. In standard cosmology, the radius of the observable universe is often given as about 46.5 billion light-years, making the diameter about 93 billion light-years. The numbers are large, yet the reasoning remains calm. The observable region is not defined by the strength of telescopes alone. It is defined by time and expansion. A quiet visual anchor supports this. A dark ocean is imagined at night. A lantern sits on a boat. The lantern's light spreads outward. If the ocean surface itself were stretching while the light moved, then the circle of illuminated water would not be a simple growing ring in a fixed space. It would be a ring on a surface that is enlarging. The light still moves at its own speed. The geometry changes beneath it. A limit of observation appears here in a precise way. There are regions beyond the observable universe from which light has not had time to reach Earth since the beginning. Those regions might exist, their light simply has not arrived. There is also a more subtle limit. In an expanding universe, some very distant regions may never be able to send light that reaches Earth, even given infinite future time, depending on the expansion history. This creates an event horizon. It is not a barrier of matter. It is a barrier of causal connection. Light-year language makes this easy to state. Beyond a certain distance in the expanding geometry, the gap grows too quickly for light to close it. A physical detail adds texture without becoming heavy. Cosmological redshift stretches the wavelength of light as space expands. Light from distant galaxies arrives redder than when it left. The shift grows with distance. Astronomers use this redshift to infer how far and how fast a galaxy is receding. This is not the galaxy moving through space faster than light in the local sense. It is the space between regions expanding. Relativity allows this, because the speed limit applies locally, not to the growth of distance due to changing geometry across large scales. A visual anchor supports redshift. A thin rainbow band is imagined on a screen from violet to red. Over time, the band slowly slides towards the red end as if the entire spectrum is being stretched. The light itself still arrives. Its wavelength has changed due to the expansion of space during travel. The light year also changes how cosmic structures are narrated. Galaxies are not distributed randomly like isolated sparks. They cluster into groups, then into clusters, then into superclusters, and they connect along filaments. Between filaments lie voids, enormous regions with few galaxies. These patterns are measured on scales of tens to hundreds of millions of light-years. On those scales, the solar system is not even a dot. The Milky Way is a small object among countless others. The unit makes the map readable because it matches the size of the structures. A limit of intuition appears again. The mind expects fullness. It expects continuous matter. The large-scale universe is mostly empty. Even inside a galaxy, stars are separated by light-years of mostly vacuum. Between galaxies, separations can be millions of light-years. The universe is a sparse network, not a crowded room. A quiet visual anchor fits the filament idea. A black page holds a web of faint threads. Bright knots sit where threads intersect. The knots are galaxy clusters. The threads are filaments. Vast blank regions sit between them. The web is delicate, not dense. The light year also clarifies a subtle point about the phrase seeing back in time. A telescope observing a galaxy 10 billion light-years away does not simply see a distant object. It sees the object as it was when the universe was younger, by about 10 billion years of light travel time, adjusted by cosmological expansion and the details of the model. In that view, the early universe appears different. Galaxies can look smaller, more irregular, and more actively forming stars. The sky becomes a layered timeline. Nearby galaxies show more recent cosmic eras. Farther galaxies show earlier ones. A physical detail about early light can be included gently. The cosmic microwave background is a faint glow-filling space, a remnant from a time when the universe cooled enough for light to travel freely. That light has been travelling for about 13.8 billion years, and arrives now as microwave radiation because it has been stretched by expansion. It is not seen with eyes. It is detected with instruments. It acts like a back wall of the observable universe, not a wall of matter, but a surface of last scattering where the universe became transparent. A visual anchor supports this background. A faint uniform haze is imagined behind all stars, like a barely visible fog that does not belong to the atmosphere. It belongs to space itself. It is quiet and everywhere. A limit of observation becomes practical in another way, because light takes time and because expansion and redshift affect what arrives. Astronomy is always a reconstruction. Data is collected as photons and particles arrive. Models connect the data to distances and histories. Uncertainty remains, and it's managed through better measurement and cross-checking. The light year remains a foundational unit within this process, because it keeps distance and information travel linked in a single consistent measure. A final visual anchor closes this section with calm scale. A wide map is imagined with concentric circles around a central point. The innermost circle is the solar neighbourhood in light years. Farther circles mark thousands, then millions, then billions of light years. Each ring contains objects seen from a different time in cosmic history. The rings do not represent travel routes, they represent information arrival. The next section will narrow the view again to the Milky Way in its size and then widen back outward. The aim will be to keep scale changes smooth, letting each step make the next one feel natural rather than abrupt. A return to the Milky Way provides a middle scale between the solar neighbourhood and the full observable universe. The Milky Way is a spiral galaxy with a disk, a central bulge, and a surrounding halo. Its diameter is roughly 100,000 light-years. The number can be held as a single calm statement. Light needs about 100,000 years to cross the galaxy from one edge to the other. That time is long compared to human history, and modest compared to the age of the universe. The Milky Way sits in the middle of scales, large enough to humble and small enough to map. A quiet visual anchor helps. A broad milky band arches across a dark sky. Dark lanes cut through the band where dust blocks light. The band is not a cloud. It is the combined glow of countless distant stars in the galactic disk seen from inside. The dust lanes are physical structures, cold grains that absorb and scatter visible light. They do not cover the galaxy uniformly. They create windows and curtains. A limit of observation appears immediately. From within the disk, dust hides the central regions in visible light. The center is not directly seen by eye. It is studied through infrared radio and other wavelengths that pass through dust more easily. This is why maps of the Milky Way are not simple photographs. They are reconstructions from multiple kinds of data. A physical detail gives the reconstruction texture. Neutral hydrogen in the galaxy emits radio waves at a wavelength of about 21 centimeters due to a hyperfine transition. This emission can be detected through dust. By measuring the Doppler shift of that line, astronomers infer motion of gas and build rotation curves. Those curves reveal how mass is distributed. The pattern also points to dark matter, an unseen component inferred from gravitational effects. The details can remain soft. The key point is that light in different forms carries information across dust and distance. A visual anchor supports the 21 centimeter idea without technical weight. A radio dish listens to a faint whisper in space. The whisper is a steady tone. The tone shifts slightly in frequency depending on the motion. The dish turns slowly, building a map from sound-like signals. The location of the Sun within the Milky Way also gives scale. The Sun lies about 26,000 light-years from the galactic centre. Light from the centre, if it could reach through dust in visible wavelengths, would be seen as it was 26,000 years ago. That was before agriculture and cities. It was during an era of hunter-gatherer life for humans. The statement is not meant to compress human worth. It is meant to show how human history fits inside galactic distances. A limit of intuition appears in a subtle way. The galaxy feels permanent and static when seen as a band of light. It is dynamic. Stars orbit the centre. Gas clouds collapse and form new stars. Supernovae seed the interstellar medium with heavier elements. Spiral arms are patterns of density waves rather than rigid structures. Motion is constant. The timescales are long. A physical detail about orbit reinforces the sense of long time. The Sun orbits the galactic centre at roughly 220 to 240 kilometers per second. That is extremely fast by human standards. It is still slow compared to light. At that speed, the Sun completes one orbit in roughly 225 to 250 million years, often called a galactic year. During one such orbit, continents shift, climates change, and species evolve. The light year becomes a unit that can connect these motions to a coherent map. A visual anchor supports the orbit. A faint spiral is drawn on dark paper. A small dot marks the Sun's position on one arm. A curved arrow traces the long path around the centre. The arrow is smooth. The movement is slow on human calendars and steady on geologic ones. The Milky Way also clarifies the density of stars. Although the galaxy contains hundreds of billions of stars, they are spaced far apart. Typical separations in the solar neighbourhood are several light years. The galaxy is not a crowded city. It is more like a sparse countryside. The sky looks full only because lines of sight pass through enormous depths of space. A limit of observation follows. Because stars are so far apart, direct travel between them is difficult. Because light takes years to cross the gaps, communication is delayed. The light year is therefore not only a mapping tool, it is an operational reality. It sets the tempo of any interstellar reach, whether robotic or hypothetical. A calm physical detail about stellar populations adds depth. The galactic disk contains many younger stars and star-forming regions. The halo contains older stars and globular clusters. Globular clusters are dense swarms of old stars, often tens of thousands to millions of stars in a roughly spherical distribution. These clusters orbit the galaxy and can be tens of thousands of light years away. Their stars are old-formed early in galactic history. They act like fossil records of early star formation. A visual anchor fits the cluster. A compact ball of light is imagined in a telescope view. The centre is bright. The edges resolve into many tiny points. The background is black. The cluster feels like a city compared to the sparse field around it, yet it is still separated from the Sun by tens of thousands of light years. The galaxy also sits within a local group of galaxies. The nearest large neighbour, Andromeda, lies about 2.5 million light years away. Even that near neighbour exists at a distance that makes the Milky Way look small on the larger cosmic map. The light year remains relevant, but larger scales often use millions or billions of light years as common units. The same logic persists. The unit keeps distance tied to information travel time. A final visual anchor closes this section. The Milky Way is imagined as a thin glowing disk seen from above. Its spiral arms curve outward. A faint halo surrounds it. A small dot marks the sun. The dot feels insignificant on the drawing, yet it contains everything familiar. The drawing does not shrink life. It expands context. The next section will move outward from the Milky Way to nearby galaxies, and the local group then return to the practical implications of communication delays across light years. The rhythm stays calm. The steps remain measured. The view widens beyond the Milky Way into a small community of galaxies. The Milky Way is not alone. It belongs to a local group, a gravitationally bound collection that includes Andromeda, the Triangulum Galaxy, and many smaller dwarf galaxies. Andromeda lies at a distance of about 2.5 million light-years. That number can be held gently by turning it into a minimum information delay. Light from Andromeda takes about 2.5 million years to arrive. The galaxy seen in the sky is the galaxy of a distant past. The past is not personal on that scale. It is geologic and evolutionary. A quiet visual anchor supports this. A faint, elongated smudge appears in a dark sky, barely visible to the unaided eye under good conditions. Through binoculars, it becomes clearer, like a soft glow with a brighter center. The smudge is not a cloud. It is a galaxy with hundreds of billions of stars. The glow is the combined light of those stars compressed by distance into a small patch. A limit of intuition appears here. At millions of light years, the phrase "far away" loses any everyday meaning. The mind cannot picture the line of travel. It can only accept the number and relate it to other numbers. The light year remains useful because it preserves the same relationship between distance and time. 2.5 million light years is both a length and a minimum look-back time in years. The unit keeps that dual meaning without additional explanation. A physical detail adds calm depth. Galaxies are held together by gravity, yet they also move within the expanding universe. Inside the local group, gravity dominates over cosmic expansion. The Milky Way and Andromeda are actually moving toward each other on average. Over billions of years they are expected to interact and eventually merge. The timescale is enormous. The idea is not a sudden collision. It is a slow dance of tidal forces and orbital decay. A visual anchor fits this slow interaction. Two faint spiral disks drift in dark space. Their outer halos overlap first like mist. Long tidal streams stretch outward as gravity pulls stars into extended arcs. The centers remain far apart for a long time. The motion is slow measured in hundreds of millions of years. The light year also frames communication in a way that changes any speculation about contact between distant societies. A message travels at light speed. A colony around Proxima Centauri would be 4.24 light years away. A one-way message would take 4.24 years to arrive. A reply would require another 4.24 years. The minimum round-trip time would be about 8.48 years. No technical improvement in radio can reduce that delay. More power can make the message clearer. It cannot make it faster. A limit of social connection appears as a quiet consequence. Across such delays, conversation becomes correspondence. Each message arrives in a different context. Situations change during the wait. Plans change, people age, decisions made on one end may no longer fit the other end by the time they arrive. The delay pushes any distant settlement toward autonomy. It makes centralized control from afar ineffective. This is not a political statement, it is a statement about information flow and decision cycles. A visual anchor supports this correspondence nature. A stack of sealed letters sits in a wooden box. Each envelope has a date. The dates are separated by years. The box is carried slowly across a long distance. When it arrives, the sender's world may already be different. A physical detail keeps the discussion grounded in astronomy rather than fiction. Even robotic probes sent to other stars would face the same signaling delays. Data return would occur years after arrival. Any time-critical intervention from Earth would be impossible once the probe is far away. Autonomous navigation and self-correction would be essential. The light year becomes not only a mapping unit but also a design constraint. A limit of observation appears in detection of signals as well. Radio waves spread out as they travel. The same power must cover a larger and larger sphere. Intensity drops with the square of distance. A faint broadcast becomes quickly buried under background noise. Detecting a distant civilization's leakage signals would require strong transmitters or purposeful beacons, and it would require the receiver to be listening in the right direction and frequency at the right time. The silence of the sky is not proof of absence. It can also be a consequence of distance and dilution. A visual anchor fits this signal dilution. A ripple spreads across a pond from a small pebble. The ripple ring grows. The wave height shrinks. Far away, the surface looks almost still. The signal still exists. It is simply too thin to notice without sensitive measurement. At larger distances, the delays have become generational. Target 50 light-years away implies 100 years for a round-trip exchange. Target 500 light-years away implies 1,000 years. The numbers remain clean because the unit is built from light travel itself. The meaning is immediate. The delays are not obstacles in a story sense. They are the natural tempo of a large universe. A final visual anchor closes this section in a calm way. A map of nearby stars is imagined as points on a dark plane. Around the sun rings are drawn at 5, 10, 25 and 50 light years. Each ring is a boundary of minimum message time. The rings are not walls, they are schedules. They show when information could arrive at the earliest if sent today. The next section will widen again to the cosmic web and the idea of a horizon, then gently return to what these scales do to perspective. The shift will remain smooth, focusing on calm structure rather than dramatic claims. The largest maps become more readable when the universe is seen as structure rather than as scattered points. Galaxies form groups, groups form clusters, clusters form superclusters. These superclusters connect along filaments, creating a cosmic web. The web is not made of threads in the ordinary sense. It is made of regions where matter is slightly denser, where gravity has gathered galaxies over billions of years. Between filaments lie voids, vast regions with relatively few galaxies. The scale of these patterns is often tens to hundreds of millions of light years. On this scale, even a galaxy becomes a small node. A calm visual anchor fits the web. A black page holds pale lines that branch and meet. At intersection, brighter knots appear. The knots are clusters. The lines are filaments. The blank regions are voids. The pattern resembles frost on glass or veins in stone, but the substance is galaxies and dark matter traced by gravity. A limit of intuition appears quickly. The mind expects emptiness to mean nothing. In cosmology, emptiness is still structured. Voids are not perfectly empty. They hold thin gas dark matter and occasional galaxies. They also influence motion because gravity depends on mass distribution. The web is a result of small, early fluctuations amplified over time. The universe on its largest scales is both sparse and patterned. A physical detail adds gentle depth. In the early universe, matter was nearly uniform with tiny variations in density. Over billions of years, gravity pulled denser regions into denser structures. Dark matter, which interacts primarily through gravity, played a leading role by forming large-scale scaffolding. Ordinary matter then fell into these gravitational wells, forming galaxies and clusters. The details can remain light. The key is that the structure forms from gravity acting on small differences over long time. A visual anchor supports this formation idea. A shallow tray of sand is imagined. Small bumps appear. With slow vibration, grains drift and gather, deepening some bumps and smoothing others. The process is not conscious. It is the result of simple forces repeated over time. The cosmic web is that repetition on a far larger stage. The light year remains central because it sets the scale of observation. A cluster 100 million light-years away is seen as it was 100 million years ago, in the simplest sense of light travel time. At that time, Earth had different continents and different species. This does not need to be emphasized as drama. It is a quiet alignment of cosmic and geologic time. The sky contains scenes from many different eras simultaneously because different distances carry different delays. A limit of observation appears in the way distance is inferred at these scales. Parallax cannot reach millions of light years. Instead, astronomers use standard Candle's redshift and the cosmic distance ladder. Redshift becomes particularly important. The wavelength of light stretches with expansion. The amount of stretch provides a measure correlated with distance and recession. The correlation is not perfect because local motions add scatter, but over large scales the trend is strong. A calm, physical detail explains why recession speed grows with distance in an expanding universe. Expansion acts everywhere. Over short distances, the additional separation per unit time is small. Over huge distances, the same fractional expansion accumulates into a larger absolute separation per unit time. This creates Hubble's law in its basic form. The farther a galaxy, the larger its redshift on average. The speed limit of light is not violated locally. The growing distance is a feature of the metric expansion of space. A visual anchor fits this accumulation. A long elastic band is marked with dots. The band is stretched gently. Every gap between neighbouring dots grows a little. Over a short portion, the increase looks small. Over the full length, the increase is large. No dot races along the band. The band itself changes. A limit of intuition follows from this. The phrase faster than light becomes confusing if applied to distant recession due to expansion. It is better to keep a strict distinction. Local motion through space is limited by light speed. The growth of distance between widely separated regions due to expanding space can exceed c, without requiring any object to outrun light locally. This distinction keeps cause and effect safe and keeps the language accurate. At these scales, the observable universe has an edge defined by light travel time and expansion history. The radius is often stated as about 46.5 billion light-years. That number is larger than the universe's age in years because the space between has expanded while the light travelled. The edge is not a boundary of matter. It is a boundary of information. Beyond it, light has not reached Earth. A final visual anchor closes the section with softness. Concentric circles are imagined around a central point labelled here. Each circle is farther in light-years. The inner circles hold nearby galaxies and clusters. The outer circles hold very distant galaxies seen in early stages. The last circle fades into darkness not because space ends, but because information does. The next section will draw these scales back toward perspective. It will connect the light year to the way human concerns fit within cosmic context without dismissing human life. The tone will stay quiet and steady. Perspective becomes calmer when the light year is treated as a tool rather than as a threat. The tool measures distance with a constant pace. It also measures the delay built into seeing. Those two meanings can soften the urge to treat the universe as either close and familiar or impossibly far and alien. The universe can be vast and still understandable. Understanding does not require emotional intensity, it requires steady scale. A quiet image helps the mind settle. A small planet is imagined as a pale marble suspended in darkness. A thin atmosphere forms a faint edge. The marble is not isolated by drama. It is simply small against a wide background. Around it the sky holds stars separated by light years. Between stars lies mostly vacuum. The emptiness is not hostile in itself. It is simply emptiness. A limit of intuition appears again in the way human problems are framed. Human life unfolds in hours, days, and decades. The cosmos unfolds in thousands, millions, and billions of years. The mismatch can feel reducing if treated carelessly. A calmer approach recognizes two truths at once. Human experiences remain fully real and meaningful on human scales. Cosmic scales remain real and vast on cosmic scales. One does not cancel the other. The light year simply makes the difference visible. A physical detail can ground this balance. Many of the atoms in living bodies were forged in stars. Hydrogen is primordial. Heavier elements like carbon, oxygen, nitrogen, calcium, and iron were formed in stellar cores or in supernova explosions and then dispersed into space. Over time, these elements became part of new clouds, new stars, and planets. Life inherits this history without needing to feel it as a burden. It can be held as a quiet continuity. A visual anchor fits this continuity. Fine dust floats in a sunbeam near a window. Each speck drifts slowly. The specks are ordinary and small, yet the elements inside them trace back to ancient stellar processes. The room is quiet. The cosmic origin is present without spectacle. The light year also reshapes the feeling of the night sky. Stars are not pinned to a dome, they are distant suns. Their light arrives after years of travel. This makes stargazing a form of looking into layered time. The concept does not need to produce existential weight, it can produce calm wonder. The sky becomes a gentle reminder that knowledge can extend beyond the limits of direct experience. Humans cannot travel to most stars. Humans can still measure their distances, temperatures, and motions through light. A limit of observation appears as a quiet discipline. All astronomical knowledge arrives through messengers. Light is the main messenger. Particles like neutrinos and cosmic rays are additional messengers, but they are harder to detect and interpret. Telescopes do not touch distant stars. They collect photons that arrive. Instruments then translate those arrivals into spectra images and time series. From those properties are inferred. The process is indirect and reliable when it is careful. A visual anchor supports this method. A prism spreads starlight into a thin rainbow. Dark lines appear in the rainbow where atoms absorb specific wavelengths. Those lines are fingerprints. They reveal what elements exist in the star's atmosphere. The star is far away. The evidence arrives as pattern. The light year also clarifies why cosmic travel is not a simple extension of planetary travel. Within the solar system, distances are large but manageable with decades of mission time. Between stars, distances become thousands of times larger. Even if propulsion improved dramatically, communication delays remain. This shapes what exploration can mean. Robotic probes can carry instruments and return data after years. Human voyages would require extreme speeds, long durations, or both. These facts can be acknowledged without leaning into despair. The facts simply guide realistic expectation. A limit of social imagination follows. A distant settlement cannot remain tightly synchronized with Earth if messages take years. Cultures drift when feedback loops slow. Decision cycles become local. This is neither good nor bad in itself. It's a consequence of delay. A quiet visual anchor fits drifting cultures. 2 clocks tick in separate rooms. Each room is sealed. A small slot allows a note to pass once every few years. The clocks may remain accurate, yet their shared schedule weakens. The separation is not hostility, it is latency. Another calm perspective emerges from the idea of horizons. The observable universe has an edge of information. Beyond it, there may be more galaxies and structures. Their light has not arrived and may never arrive depending on expansion. This creates a humility about what can be known. It also creates a clarity. There are limits that do not depend on effort. Knowing those limits helps focus effort where it matters inside the region where evidence can arrive. A final visual anchor for this section keeps the tone soft. A shoreline at night fades into fog. The fog is not a wall, it is the limit of visibility. Beyond the fog, the sea continues. The observer does not need to see everything to understand that the sea is vast. The horizon is part of the scene, not a failure of sight. The next section will close the full sequence with a gentle landing. It will restate what a light year is, why it is used, and what it changes in the way the universe is held in mind. The ending will remain calm and complete with no lingering cliff. The journey ends where the measurement begins with a simple unit that becomes a steady companion in cosmic thought. A light year is the distance light travels in 1 year. It is not time, even though the word year appears in the name. It is a distance built from a constant speed and a familiar calendar. Light moves at about 300,000 kilometers each second in vacuum. Multiply that pace by the seconds in a year, and the result is about 9.46 trillion kilometers. The number is large, yet it does not need to be carried as a burden. The light year exists to make the map readable. A quiet visual anchor settles the definition. A straight line is imagined in darkness. Along the line, small marks represent seconds. The marks are too many to count. The line remains straight and calm. The year is not a feeling. It is a count of consistent steps. The reason the unit matters is practical. Astronomers measure distances between stars. Those distances are naturally on the order of several light years. In kilometres, the same distances become long strings of digits. Those strings are correct and awkward. A light year compresses the same truth into a form that holds ratios and comparisons. 4 light years is near, 40 light years is farther. 400 light years reaches into a larger neighbourhood. The unit returns shape to distance. A second reason the unit matters is conceptual. Light years quietly tie distance to information delay. When a star is described as 25 light years away, the statement also implies that the arriving light began its travel 25 years earlier. The sky becomes layered time. Nearby stars show the near past. Farther stars show deeper past. Distant galaxies show the early cosmic eras. Telescopes are instruments for collecting delayed light. They do not show the present of distant places. They show the information that has arrived. A calm physical detail supports this layered view. Photons carry energy and momentum. They also carry information in their timing, direction, and spectrum. Along the journey, photons can be scattered or absorbed. If they survive, they arrive and can be measured. The measurement is not a guess. It is a record of what reached the detector. Distance is then inferred from geometry, calibrated brightness, redshift, and other careful methods. The full process is an accumulation of evidence. The light year is one of the basic units that keeps the evidence organised. A quiet visual anchor fits the record idea. A camera sensor is imagined as a flat grid of tiny wells. Each arriving photon triggers a small response. Over time, the grid fills with a pattern. The pattern becomes an image. The image is a history of arrivals, not a direct touch of the source. The speed of light also sets limits that shape everything discussed. No signal can arrive sooner than light travel time across space. No command can be answered instantly across interplanetary distances. No conversation can be immediate across light years. The limit is not a flaw. It is the tempo of the universe. The same limit also protects cause and effect in ordinary conditions. Relativity emerges from the insistence that light speed is constant. Time and distance adjust to preserve it. The light year built from that constant inherits this deep consistency. A gentle perspective follows without diminishing human life. Human concerns occur on small scales. They remain meaningful on those scales. Cosmic scales add context rather than judgment. A planet is small, yet it holds the entire known story of life. A star is one among billions, yet it is the source of a system's warmth and stability. A galaxy is one among trillions, yet it carries long histories of starbirth and element creation. The light year allows these scales to be narrated with clarity rather than confusion. A final visual anchor helps the mind rest. A clear night sky holds points of light. Each point is a distant sun. The points do not rush. The darkness between them is deep. The light arriving at an eye has travelled for years or centuries. The observer remains still. The universe offers its record slowly and steadily. The measurement that once sounded mind-bending becomes quiet in the end. A light year is simply a distance that matches the size of the cosmic map. It keeps numbers readable. It keeps distance and delay linked. It turns the night sky into a place where space and time are always intertwined, not by mystery but by the simple fact that light takes time to travel. That fact does not need excitement to be profound. It can sit calmly in the background like a steady heartbeat of physics. Buenas noches.